Hello students, today I'm going to show you the shape of sound. So we all know our ears can have different shapes, as you can see here on the lynx, on a hare, on a donkey, on a monkey, on different animals, okay, like this beautiful desert fox, tiger, or even the human ear. So we have different shapes of ears, but how does a sound looks like? Okay, so we know for the ears, but what about the sound? So I'm going to show you a little video. If you don't see it well through this screenshot, you can find a link in my email. But when you use a special camera and you clap your hands, you know that a sound will be produced. But how does it look like? If you look at it here, you can see that we have some little vibration, okay? Now, these vibrations are produced by the movement of air. So when we look at the vibration we produce through our hand, oh, I'll need to minimize that, otherwise you don't see my mouse. So imagine the speaker being the hand clapping. What are we going to do when we clap? We're going to move air, molecules of air around. So some will be compressed. We're talking about molecules or atoms if you want. And some will expand. So it's like pushing something. Because you're pushing it, it's going to compress with what's behind it. There we go. And then by doing that, they'll give enough energy for the rest to just continue moving. So it's going to move through air by compression expansion. Okay. What I care is that you understand, how do we transform this mathematically? We're going to transform it by using an XY axis. Here you don't see the XY axis, but you see that movement of compression. The compression will be transformed by a high peak, and an expansion will be expressed mathematically by a low peak. So we get some high peak, low peak, like if you were vibrating a rope in front of you. Okay, we would have some high peak, some low peak, some high peak, low peak. So we have transformed something in 3 dimensions into 2 dimensions using mathematics. Now, what could we say, or what could we observe on this new graph? This. Like me right now speaking to you, it would look like that on a software specialized with sound. So we get some high peak, low peaks, extremely close to each other because I'm using a lot of letters next to each other. So it's quite too complex. Let's look at something a little bit simpler. We have 3 compression and 1, 2, 3, and maybe a last one here at the back, expansion, which means we're going to have 3 peaks and some low peaks. And if you remember the activity you've done in Science-Based Explore, you discovered some new words. One was wavelength, okay, the separation between these peaks or between these compressions, sorry. And you discovered maybe another word called amplitude. What do they mean? Let's try to separate them to really understand them. The amplitude, it's the intensity of a sound. So I can talk to you like this, or I can talk to you like that. What does it mean? It means that I'll give more energy to the system, to the molecule of air around me, so it's going to give a high amplitude. So the difference between the space between a crest and a throat will be much bigger. So high amplitude will be a loud sound. What about a quiet sound? It means I'll give less energy to the environment, to the molecule of air, so it's going to be a low amplitude, which means the space between the crest and the throat will be extremely low. This is what we call the amplitude. So thanks to a graph, we can visually see the amplitude, which means if we can visually see it, we can measure it. And there's a famous guy called Mr. Decibels, as you can see here in the middle of the screen, that made a scale. In this case, it's between 0 and 200. It could be much higher than that if we want. Okay, imagine the explosion of the Big Bang, how many decimals it would be. But in this case, a 20 would be the tic-tac of a watch, and it would be extremely low in amplitude, which means it's going to be low in decibels. A gun firing would produce a huge amount of energy, which means it's going to produce a huge amount of decibels, which means the amplitude between the crest and the throat would be extremely big. Now, what about the amount of waves that we have, the amount of vibration that we have, the amount of expansion or compression that we have? This is what we called the wavelength or the frequency. So if we have some very short wavelength, it means that we're going to have a lot of waves per second. This is what we call the frequency of a sound. How does it sound like it's a high pitch? So it's going to be talking like this, okay? So I'm not changing my intensity, I'm changing the amount of vibration per second. Well, here on the second graph, you can see there's less vibration per second. There's more space between each wave, so the wavelengths will be much bigger. And how does it sound like? It will be a low pitch, low frequency. It's gonna be like this. Okay, the voice more of a man, where high pitch will be more the voice of a woman, okay, or of a child. So if we can visually see it, we can measure it. And the guy who came up with the idea of measuring the amount of wavelength per second was Mr. Hertz, very famous for the car renting, but there is no relationship with it. And the pitch is measured in hertz. So as you can see here, bass sound will have a very low frequency. Treble sounds, which are, or ultrasound, maybe you'll understand it better, which has a lot of energy, lots of waves per second, lots of vibration per second, will have a huge amount of hertz. So what do I want you to do on a piece of paper? I would like you to draw 7 different graphs, and on each of these graphs to draw a little wave from left to right, showing me how would it look like. Here we go. What would silence look like on a graph? An electric guitar, a bass guitar. If you don't know the sound or how do they sound like, just go on YouTube, write electric guitar example, and you will normally hear, what is it? A rock concert. I'm not talking about a classic concert, I'm talking about a rock concert. What about a woman talking versus a man talking? Use 2 colors on the same graph, same for the child versus the man, or someone whispering. Okay, I'm going to give you all the solution on Friday. So right now, based on the amplitude and the wavelength, you should know what to draw on each of these graphs. Thank you very much, and I hope you understood it, because it's a difficult topic, because it's extremely abstract, it's involving a lot of math, and in this case, geometry. But I hope you understood it. Thank you very much.